Okay, so by now I'm hoping you're asking yourself questions like, well, how do you know that much about the universe? How do we know about, all these things you're talking about? And especially today, we're going to address the question of how do we know what the universe was like in the past? And to spoiler alert, we do get these questions from the light. It's the light that tells us what's what's happening. Why is that? It turns out, all right. So light is the one that offers us the answers, and the answer is in how fast light travels. Okay, so light travels really fast. This is its speed. We're gonna write it also in scientific notation because it's very useful. There are some examples on this C, the speed of light, and how to write that in scientific notation in the math skills page. So don't forget to check that out. So we have, instead of writing 300,000 kilometers per second, it's going to be 3 times 10 to, what power is going to be 1, 2, 3, 4, 5 zeros. So this is what we're going to have, kilometers per second. Now, very useful sometimes to write it in meters per second. So just remember that a kilometer, that is 1,000 meters. So in scientific notation, very useful. That is 10 to the 3 meters. So if we put it together, so basically instead of 1 kilometer, we're going to have 10 to the 3 meters. That's going to be 3 times 10 to the 5 times 10 to the 3 meters per second. Put this together just as you might have been reminded of in the math skills. So we're going to add the exponent. So the result is 3 times 10 to the 8 meters per second. Also in the math skills, you will find out maybe, for example, if you're interested, how fast light is in miles per hour. Just as a very good comparison as to just how fast, say, you're driving when you go shopping or going somewhere else to where you need to go these days. Okay, and it turns out, I don't remember that exact number, but you can find it in the math skills page. It's also 10 to the 8 something here. Okay, so it's really fast. It's fast, right? The light travels really fast. So as we will learn in, I think it's chapter 5, we'll learn that actually all of the information that we gather, especially the things that are far away from us, we don't touch them, it's coming through light. So basically, information about, say, your very close friends or things around you, they come through you via light, but because they're very close to you, you seem like you're getting that information instantaneously. But for example, right, so you have Earth to Moon. There's quite a distance between those two. It takes light 1 full second to travel, okay, that distance. How about Earth to Sun? Well, guess what? It takes 8 minutes for that. And say the star Sirius. You probably heard about that star Sirius. Seriously, it takes 8 years for light to travel from Sirius. As soon as that light is produced and escapes the surface of Sirius, it's going to need 8 years to travel at that fantastic speed, right? Or this, if you want, right? So see, that is the speed of light. It takes 8 years. Okay, how about the closest galaxy to our own Milky Way? That would be Andromeda Galaxy, 2.5 million years. So what is it that we're actually gathering here is that we're actually seeing things as they were in the past. And the further things are, the further away, the further back in time are seeing. So basically, we see Andromeda as it was 2.5 million years ago. We see the sun only as it was 8 minutes ago. All right? So armed with this new information, all right? Actually, before we do that, because I forgot, you realize that, these distances, these huge distances between us and the moon, us and the sun, us and the closest galaxy to us, or which is Andromeda galaxy, or other types of galaxies or quasars or other things that are really, really far away, right? We're going to need, or it's going to be very useful to come up with a new ladder for measuring distances. And that is going to be the distance that light can travel in 1 year, right? So a distance, or 1 light year. Okay, so that is distance. And how are we going to calculate? It's a distance that light travels in 1 year. Distance is speed, average speed, times the duration of that motion, which is the time, right? So in our situation, we want to calculate the distance traveled by light. So the speed is c, which is 3 times 10 to the 8 meters per second, and the time is going to be 1 year. All right, so we're going to have a multiplication factor here. It's going to be really hard to do the multiplication unless we're matching some units. And for that, I see that we can actually try to match these time units, the second and the year. So for that, we're going to try to convert that year into seconds. How do we do that? Okay, so remember, 1 year, we can probably write it in terms of how many days. That's going to be 365 days. Each of these days has how many hours? 24 hours. Each of these hours has minutes. That's going to be 60 minutes. And each of these minutes has 60 seconds. So if you kind of put them all together, each hour, right, has how many seconds? It's going to be 60 times 60, so 3,600 seconds. All right, you do it the same way. If you want to convert 24 hours into seconds, that's going to be 24 times 3,600 seconds, and you keep going. So 365 days is going to be 365 times 24 times 3,600 seconds. Okay, so now you do these calculations, and I'm just going to show you a good way, easy way to do it, even without the calculator, and this also kind of showing off the power of using the scientific notation in the powers of 10. So 1 light year, 1 light year. That's another way of abbreviating this. So what do we have? 3 times 10 to the 8, that was meters per second, right? It was the first member of this multiplication. And then we have that year, we're going to write it in seconds. So we have times 365 times 24 times 3,600 seconds. And you see how those seconds actually can cancel. So we end up with the meters, which is a perfectly good unit for a distance. Distance, the light year is distance. Okay. All right, so here's what we're going to do. We're going to write all of these numbers in scientific notation, starting with this one. This is 3.6 times 10 to the third. This is 2.4 times 10 to the 1. And this one, for example, is 3.65 times 10 to the 2. And now we're going to use the fact that the multiplication is commutative, so it doesn't matter in which order we're actually proceeding with the multiplication. So we're going to first use these numbers. We're going to multiply them together, okay? So 3 times 3.65 times 2.4 times 3.6, and then we have the leftovers, right, which are the powers of 10. When you multiply them together, you end up with 10 to the power of 8 plus 2 plus 1 plus 3. And the units are going to be meters. All right, so you do all these calculations and you end up with, what's going to be here? 10 to 8 plus 2 plus 4, that is 14 meters, right? And what do we have here? So 2.4 times 3. Just do those calculations. What do you think you're getting? 32 something, right? 3 times 3. So about 10 times 10 times 10. I think this is it, okay? Like 3 times 30 something, right? Okay, so I wrote it like this because I wanted to keep the powers of 10 and the scientific notation. So here's what we get. 10 times 10 to the 15 meters. If, you know, sometimes in your homework problems, you might need it in kilometers. So it's 10 times 10 to the 12 kilometers, because I got 3. You got a minus 3 to go to kilometers. So, hey, this is what you get. The light year is about 10 trillion kilometers. Of course, you can convert that into miles as well, and you're gonna find that that is 6 trillion miles. So yeah, that's a huge distance, but hey, it's much easier to say, hey, you know, there are a few light years until you know, that you need to travel to find the closest star to us, for example, the Alpha Centauri, or you have a few hundreds of light years to find some other stars, or you know, 1,000 light years to find that galaxy and so on, right? Which is easier than just to say, oh, you know, there are these many billions of trillions of whatever miles, right? So it's very useful. It has, okay, so this is another way of looking at the calculations. You can pause the video and compare the calculations we've done in the previous page with this one, if this looks more readable. Okay, so now I have a question. Say we're looking at the Orion Nebula, which is this one as seen with the Hubble Space Telescope, which is a bunch of gas where stars form. Okay, it's a very famous nebula, and it's somewhere here under, under the Orion belt. Okay, so this is just the Orion constellation. Some place in the sky. We're going to talk in the next chapter about constellations. All right, so the question is, when will you be able to see what the Orion Nebula looks like now? Okay, given that actually what we see now as Orion Nebula is how the Orion Nebula looked like 1,500 years ago, because it does take light 1,500 years to travel from that place to us. And the answer is obviously in 1,500 years. All right. some students, I know they could get trapped into a problem here and might say, oh, that's going to be in 1500 light years. Now remember, this is a measure for distance, right? And so that's not going to be a measure of when will we be able to see how the Orion Nebula looks like today. So just, an example of how you need to pay attention to what you answer in the question, especially in the exam, right? In the homework, you're going to have the chance to correct your answer if you get it wrong the first time. All right. So as I said, at greater distances, we see objects as they were when the universe was much younger. That is, in the past, when the universe was a different stage in its evolution. Okay? So, for example, this galaxy, we see it as the universe was in it, as that galaxy was about 7 billion years ago, because it is at that distance of 7 billion light years away from us. Same for this one, and you see, this is this is just a schematic of how the universe looks like, and this is a much better shaped form galaxy. This is a galaxy that is much further back in time, so very close to the very beginning of the universe. We believe that this is, maybe close to being a proto-galaxy. So maybe it didn't have enough time to form and have the shape that we are used to see around us for galaxies. And so it turns out we can see the entire visible universe, okay? So we can see as much as the light was able to travel in 14 billion years. We cannot see past that, okay? So this is basically the edge of the visible universe. That kind of ties back to some things we talked about previously. All right, so that's it for now.